Okay. Hello all. Can you hear me? Okay. Yes. Perfect. Okay, that's good. We need this one now. Let's see who's in the class. Okay, let's get started. Hello everyone. I see many students in the class. Thank you for coming to the class. We don't have attendance today, so yeah, but it's good to be in the class because next week we have exam, Monday. So we're gonna solve some questions that very related to the exam, so it's good. So let's see what we had last class and what we're gonna have today. So everything okay? Can you hear me good, everybody? I already tested. I think I'm okay to go. So yeah, people saying all good. Is there an attendance quiz for class? No attendance today. But don't leave the class because of attendance. Okay, let's see what we have today. Today we're gonna have some extra information about instruction set. Instruction set, we started instruction set for RISC-V. Before starting the class, actually I wanted to mention something about your assignment, second assignment. For second assignment, last question, question 4, I asked actually to, it was multiple instructions in RISC-V, and I asked to specify some fields, like for example opcode or I don't know, function 3 or function 7 values. I don't know how you found them, but nobody asked me. Probably you all figured that out probably, or I don't know. You could always check book, like a reference book. We know we have a reference book. Is actually Peterson book. I think it's fundamental of computer organization. It's called that, RISC-V. And you can find this information like opcodes for instructions over there. Another way to could find those informations, however, most of information were available in the instruction, like for example register source, register destination, or you know, immediate values. In those instructions you don't need to know those information. They are not many conventional information, but information that you should know is you should know that were not available inside the instruction was opcode and function 3 and function 7, that you could find them in reference book, or also sometimes if you need to find those stuff, you can use those simulators that I introduced to you. I think 2 simulators I mentioned last class. I work with Berkeley University simulator that called Venus. And the other one that I introduced in your assignment was Cornell from Cornell University. I think this Venus one is better. Yeah. So maybe you could use that, write the code, and it's going to show you exactly the binary representation of that instruction. Instruction like assembly code need to get the binary to can execute using the machine. Okay, that was something that I wanted to mention. But in exam, of course, you can bring one paper. You can have one paper like this size, and you can write two sides of that. It's a actually cheat sheet. You can fill it up. But I don't want you print all the slides in one because I'm not gonna ask questions about the slides. If you want to learn, the best way is to write them with hand in this. You can write it very small because when you write this up, you're also practicing. This is what I like you to do. Because in another exam that I had with another course, I realized the students just printed all the slides, very, very little, and that's not going to help you. And it's going to be so hard to find the simple things. The best way that you can take advantage of this cheat sheet is to use them by yourself, write them by yourself. I prefer to write by hand, and any part that you don't know, when you know something, you don't need to write it here. And yeah, that's something that I wanted to mention before going to the next part. Yeah, any question about these things that I mentioned? Okay. No question? Okay. Let's get started. Another thing in that example actually was something about U-type question, U-type instructions, because we didn't explain about U-type. U coming from upper immediate type. We have multiple instructions that using upper immediate, because immediate side was 12 bits, as you remember. But upper immediate is 20 bits. We didn't introduce any instructions regarding to upper immediate type yet, but today we're going to talk about one of them, that is jump. We have a jump instruction. A jump is type of changing the control flow without checking any condition. A branch is with condition, like we are branching if it's equal, branching not equal, greater, less. But jump doesn't have any condition. You just jump. So this jump doesn't need lots of operands, just need the address, the label that wants to jump. So this jump instruction consider U-type instruction or UJ type instruction, ultra immediate. And we have another ultra immediate that is called load upper immediate. We didn't talk about that, so. But in that example, because I took that example from the book, inside the last, the questions of the book, so it mentioned write these fields like opcode, source, destination, immediate for the instructions that are not UJ type or U type. None of them was this UJ type. So I just wanted to mention this too, because nobody asked me questions, so I know you all found it out. Okay. That's it. So, but today we're going to talk about jump. Yeah, jump. Like without any condition, just jump. We're going to talk about that, so that's done. So, what else we talked last class? We also last class talked about actually logical operations. These logical operations like and, or, XOR, an AND immediate, or immediate, or XOR immediate. They were simple, but sometimes it can get complex when you are mixing them together when you want to do, because with these instructions you can do bit manipulation, and also you can work with bytes. As you know, this RISC-V instruction, this RISC-V computer is like a 64-bit processor. So all the registers are 64 bits. But sometimes you need to work with a byte, or actually words, or half word. We also have half word. Half word is 16 bits. Half word is 32, and double word is 64. So we also have HW. HW is 16 bits. So we have a word that is 32 bits. We have byte. Just going to put B. 8 bits. We have half byte, a half word, and double word. 64. Sorry, 64 bits. So I just wanted to mention this. So we have half word as well. So let's see if I can make this smaller so you can. Yeah. Oh. Not that one. Doesn't matter. Okay. Why it's not showing my picture? Okay, maybe this is better. Yeah, no problem. Okay, so so that was something that I wanted to mention. Okay, so that's a logical operation. For logical operations, shift also consider a logical operation. We can mix or combine shift and this and or and XOR for other purposes, like for extracting bytes, for example. We saw a couple of examples last class. Let I clean this up. Another thing that before going to the next topic I want to mention, we talked about shift left logical or shift right logical, but we also have shift left arithmetic and shift right arithmetic. So arithmetic is it means that just for sign numbers, when you are consider arithmetic, when you are shifting one register, it keep the sign. If it's negative, it stay negative, and it's positive, it stay positive. We also can have shift left arithmetic immediate and shift right arithmetic immediate. Let's just have example, because we didn't mention anything about this arithmetic before starting the new topic. I want to have this example. Imagine we have a register X1 that has these values. So 1, 1, 0, 0, 0. Okay, it's 64 bits. Okay, this register X1, if you remember, X1 has a certain characteristic. X1 is a type of register that we are considering return address on it. Okay, but here we don't care about that part. Okay, but in general, anytime we use X1, X1 is a return address. What is return address? When you are, for example, calling a procedure or function, you know, you always save the return address in x1. But we're going to talk about that later. But anyway, in this example, we have register x1, this value. We don't care what is this, okay? But we want to do something. We want to shift this, shift right, logical, immediate, x1, 2 bits, and put it in x2. Okay, they are all operands. These two are source operand, and this is destination. So we are shifting x1 to the right 2 bits and put the result in x2. Okay, so we want to do this operation. So what's going to happen? So as we explained before in last class, when we are shifting to right, we enter 0 in most significant bit part. This is least significant bit. Okay, so we enter 2 0 here and 1 1 1, all the 1 1 0. So that's gonna be x2. Okay, because we shifted 2 bits, 2 zeros gonna get out from the other side, and this is the value. Okay, that was for shift right logical. What about shift right arithmetic? So I'm just going to change this color to another one. Shift right arithmetic immediate, x2, x1, and 2. Same thing, same operation, same values, and x1 is still this. Okay, if we run this instruction, again we are shifting x2 2 bits to the right, but because this value is a negative value, because this is a negative and this is arithmetic shift, we need to keep the sign. So instead of entering 0, we enter 1. That's the difference between shift arithmetic and shift actually logical. So it was obvious, but I just wanted to have one example. If you see something like that in your exam, don't get too excited. That's it. Okay, so we talk about this. We also talk about conditional operation. We introduce that. We're going to talk more about condition. Condition is, can be complex. We implemented if and else last class. I think we talked about loop as well, but loop, we have different loop. Like we have while loop, we have for loop. They are a little different. We can talk about them more today. And if we get the chance, we're going to talk about procedure call as well. So maybe not. Anyway, this procedure call is not part of your exam next week. So exam gonna be till here. This is not part of exam. Okay. We don't have, maybe I don't cover it at all today. And another thing that before started, I need to mention the new assignment. I'm gonna put a new assignment tonight, just regarding to these sessions that we had, especially about logical operations and conditional operation, and that and the due date is the next Wednesday. But it's good to do it before exam, because exam might be very similar to some of those questions. So please do the assignment that I'm gonna post tonight as soon as possible. Don't leave it actually for next week. And if you have any questions, just send me email or whatever. I will answer. Even during these holidays, I will answer your emails. That's it. Okay, so let's do a recap about conditional branches. So condition is so important in programming. We know without condition we can't call a programming language really a programming language. Is add lots of advantage to programming with condition. Anyway, condition is when conditional branch is when you are changing the control or the normal program flow to somewhere else. You know, when the normal program flow is one instruction after the other. So that's a normal flow. But you are changing this program flow by comparing two registers. You're comparing two registers, and if, for example, these two registers, if this condition is correct, you're jumping to somewhere else. Those who are, for example, jumping somewhere else. So in this case, you can make so many new actually conditions in your program. You can make a loop, you can repeat something many times, you can check some stuff, you can just, if the condition is not okay, you can just finish the code and add lots of properties to your code. So that's conditional branch. When we are talking about branch, it's also changing the control, but in branch you always have a condition. When we are talking about jump is also kind of changing conditional, changing the control or changing the program flow. But in jump we don't check any condition. So anyway, so branch has different type. Branch equal, branch not equal. Branch equal is just like, for example, if register 1 is equal to register 2, or register I is equal to register J, go to label that we have. And if this label is something that assembler specifies. It's like a when you are writing a code, here is a program counter. This is program counter. This is the one number here specify which instruction is there. You have a memory called instruction memory. Instruction memory. And from this instruction memory, each instruction fetch to the CPU and get executed, and then go to the next instruction. This program counter is adding, because these instructions are 4 bytes. So after executing one instruction, program counter increased with 4, and then go to the next instruction. So this 4 coming from 4 bytes of each instruction. All instructions in this architecture that is RISC-V is 4 bytes. We know that. Okay, so it's a regular thing. So, and they are all similar. We don't have different size for instruction. They are all same size. Okay, so that's something that we need to consider. So this label who put, for example, these labels to numbers, assembler. Okay, that's the important part. So we also have branch not equal. If you have any questions, you can just type your question in the chat, or ask me if you want. Anyway, branch not equal is same way. If it's not equal, we are going same way. How we can write that? Example is write that branch not equal. For example, x 10, x 2, label done. Okay, label done is something that later assembler gonna put a number there. Okay, and if register x10 is equal to is not equal to x2, we are going to done, something like that. Okay, so we already talked about this, so that's why I just wanted to do a recap. We also have other type of conditions when we want to check greater or less. We have branch less than, and branch greater than. So we also have these two, same way. So when register 1 is less than R2, we are jumping to the label, or when register source 1 is bigger or equal to X2, we are jumping to label 1, for example, in this example. So example, like imagine we want to implement this. If A is bigger than B, we are incrementing A by 1. Okay, so first we need to see which register bind to which variable. So binding is a main thing. We always need to know that. In this example, A is X22 and B is X23. Okay, so these two variables that we are using, we are binding them to one because A and B are not real, you know. We are assigning that to the real place in the computer. How we do that, that's called binding. So we bind them in this, it's given. So we are imagining this is given. So what we need to do, we are checking if A is bigger than B. We are going to label, for example, called, okay. So what we need to do, anytime we have a condition, if the condition is not true, we are going to exit. So we need to have one label called exit, or sometimes we call it done. You know, if it's for loop, we always have done. Anytime we have if, we just need one label, because when the condition is not actually true, we need to get out of the we don't need to run that code. Like for example here, we don't need to increase A if the condition is not true. So first we need to check the condition, but we are checking the negate of condition. We are checking, okay, here we are saying A is bigger than B, but we are checking if yeah, branch great or equal if B is equal to, if B is greater or equal to A. So negate of that gonna be this. So X23, that is B, X22, that is A, go to exit. So this is the negate of the condition. Condition is A bigger than B. Negate of that is B bigger or equal to A. So so maybe I write it like that. So negate of this is equal to this. So this is important. We always need to check the negate. If the condition is not allowed, we just get out, because we don't want to go to the loop if the condition is not true. So we go to exit. Other than that, we are increasing A. What is A? So we are adding immediate, just one to A is X22, and put it to X22. That's it. So this is how we are implementing if. So we had that before. I just wanted to systematically explain it, how we need to do that. So we are checking the negate. That's the important part. So negate of A bigger than B is B or A smaller or equal to B. So maybe like that. Okay. So any question about this? Okay, so that's another version of that in a better, cleaner version. It's exactly the same. Okay, we also, last class, we also talked about else, how we can have if and else. So if we have else, that's also easy. Like if you see this flow chart, if, for example, the condition is to checking I and J. If I and J not equal, is actually else condition, and if it's equal, is just the condition is true. So first we do binding. So binding, we are considering that for each of these registers we have one variable, and so to write this in assembly, again the same way. When we have condition, we find the negate of that. So j equal to I is equal to j, negate is I not equal I not equal to j. So maybe I write it like that. So, and this is coming from branch not equal. Okay, so as you can see, we are checking the negate. If these two are not equal, we go to else and done. So we don't need to write. If it's equal, if the condition is not true, we go to the next instruction, and the next instruction is adding G and H, and the next instruction we need to jump from else, so we need one unconditional branch or jump. We also can have jump. So how we write jump, we have instruction for jump called actually jump and link, JAL. Okay, jump and link, jump and link. Why is called jump and link? I will explain. This jump and link is a UJ type instruction. As you can see, it just has need two operand. One is one register. Here we consider x0. It can be anything, and exit is a label. So it means we are jumping to exit without any it's not a conditional jump. It's unconditional. But why we have this x0? This x0 is just for saving the next program counter. So we put x0 here because we don't need it. But normally we put x1 here. But if we put x1, what's going to happen? If, for example, the program counter, when we are running this code, program counter is here, program counter. What this jump doing, adding program counter with by 4 and put it in program counter. So this is, program counter and put it in x1. This is what jump and link doing. Well, you can see here, right? Okay. So as you can see, this jump, the load part, jump and load, the load part coming from this is loading program counter to the register that we specified. What register is x1? X1 is actually a very specific register. We always use x1 for saving the next address, program counter, the return address actually. So, but here we don't need it. We don't want to come back. We just that's why we can put x0 as well, because x0 is always 0. Even if you put something inside, it's not going to change. Anyway, okay, so in this example, instead of using branch equal x0, x0, exit, you just can write this instruction, and both same, nothing going to change. They are both need one clock to execute, for example, maybe not clock, like time slice, or whatever. They are equal in terms of running. none of them is slower or faster. Okay, any question about that? Let's see. Can I see the here? Okay, I see one. Okay, good. One new. Okay, no, nothing. Okay, so let's go for next slide. Okay, yeah, here also I mentioned that assembler calculate these addresses. I mean these labels, assembler specify these addresses, because they are, we don't have exit, we don't have else, we just have numbers that specify instructions in instruction memory. We have a memory called instruction memory, and the program is there, instructions are there, and those instructions have one address in this memory, and it's called program counter that specify which code need to get fetched. Every instruction that get fetched, program counter go to the next instruction. But we can play with that, we can change that using, or we can save the program counter value using this jump and link instruction. Okay, anyway, let's go to another instruction, another example. Okay, we are going to the loop. Loop, we have two types of loop. One is while loop, and one is for loop. Okay, in programming you had those two, you know. Maybe you ask me, why Behzad, why you are teaching this thing? Where are we gonna use them? You know, we're gonna use C++ or Python, and why we need to know assembly? You know, the point is, you are supposed to be a computer or electrical engineer. You know, I want to see my face. Let's see. Okay. You're gonna be a computer engineer or actually electrical engineer. Maybe in your life you want to design a processor. If you want to design a processor, in processor you need to know how these instructions get executed and how you can design this instruction. You need to know this stuff in these details. Maybe later, if you want to design a new processor for your specific application, maybe it's not a general purpose processor, it's a very specific processor for your application, and you need to do same things. Maybe easier, because you don't need lots of instruction, maybe some specific instructions. And that's why you need to know these details. And believe me, this is going to help you also. If you don't design a processor, it still is going to help you to understand other part of computer much better with a broader view, and it's going to help you to understand other things. That's why you need to know this stuff like assembly. And also another point, you can understand also how compilers work. You know, when you are using with an interpreter like Java or actually Python, or a compiler like C++, for example, or C. So you can understand why, for example, some compilers are fast, some compilers are slow, and why? Anybody know why some compilers are slower than others? Anybody? Any response? Any idea? Or maybe we just say compiler. We don't go to interpreter. Of course, compiler is faster than interpreter. Anybody knows why compiler is faster than interpreter? I think we mentioned that before. Any idea why compiler is faster than interpreter? Okay, I can mention that. The reason is the compiler is actually changing the high-level language to the assembly language in a very optimal way. It's not do one by one. It's not changing one instruction to multiple instruction in assembly. It's consider all the things at the same time and can optimize it better, But even between compilers, like for example, C compiler, many companies design C compiler. Like Microsoft has one. I don't know, many other companies has different, compiler for even C++. So, but some of them are faster, some of them are actually slower. The reason is how they change these high-level languages to the assembly language to can get executed by the machine in a very better and optimal way. So that's why sometimes you find a find a compiler is so cheap compared to some compilers are more expensive, because they can make actually better performance code that can execute faster or less waste less memory or resources. Anyway, that's the reason. Okay. Okay. Let's finish this part, and that is very important in loop. Even in the loop that is repeating like 100 times or maybe 1,000,000 times, one instruction is important. When one instruction can make performance a lot, because as we explained before, performance is depend on number of instructions that can get executed. This number of instructions is important, and if it's less, of course, it's faster. Okay, so we have two types of loop: while and for. While loop is actually this example that we have here has an array. So maybe I do another example that doesn't work with array of memory, just a normal. So imagine I ask you implement this C instruction in assembly. I is bigger than 0. Do one variable ACC, add it by 2, and then we have I minus. Okay, so we have this C instruction. What is doing? Checking as far as I is bigger than 0, incrementing the ACC by 2, and decrease I, and repeating many times. So that's a while instruction. Okay, so how we can do that? Anytime you need loop, anytime you want to implement loop, you need two labels. For if, you just need one label that is showing the end. But for loop, we need two labels. One is in top of the label, the top of the loop, and one is at the end. So we call it done, for example. Okay, we have one loop that because we are going up and repeating and repeating. Similar to if, here also, because we need to check the condition, we consider the negate of condition. If it's I bigger than 0, we consider if it's equal. Branch equal. Okay, another thing is we need to do binding as well. So consider I actually x6 and consider ACC x5. So we bind I to x6 and bind ACC to x5. So we check I, that is x6, by actually 0, that is x0 is always 0. If this is equal to 0, we are going to done and done. other than that, we need to add add immediate x5 by 2 and put it in x5, and then decrease decrease I. Decrease I, we can add just minus I, is gonna be like a decrease. Add I x6, because x6 is I, minus 1. Okay? Okay, that's good. So this is the loop that we come in here. But right now we need to jump to the loop here. And this jump doesn't need to be conditional. You can use jump and link. Jump and link, x0 and loop. We also can use branch. For example, you can use branch equal and put x0, x0 loop, because x0 and x0 are always equal. So it's like an unconditional branch. So, but jump is also work. So this is implementing this while loop. Okay, this was for loop. Before going to this example that using memory, let's do for as well. Let's have another example. This example, we are trying to write assembly code for this C code for I is equal 0, I less than 10, I plus plus, ACC plus plus. Okay, so I ask you, for example, in exam, implement this for instruction in C++ using RISC-V assembly code. Okay, so let's do that. So similar to anytime you need a loop, you need to implement loop, you need two labels. One in top of label, you always consider that loop. And one, okay, before that, we need something else here too. We need initialization. We need to initiate I. Okay, so we need one instruction for initiating I. Okay, again, I is x6 and ACC is x5. So this is binding, that we consider that. Similar way. Let's change the color. Let's make it, okay. So we have loop. We have actually initialization, add I. So that's called initialization. Because we have one variable or index, we call that index too. Index initialization. Add I x6, because we want to load 0. We don't have load in RISC, but we can do it with add, with x0. So this is actually doing I is equal to 0. So this is initialization. Okay. So we are adding these two. We are adding these two and put the result in this. Okay. And because x0 is always 0, is like a load. We need to label. One is loop, one is done. Label has a colon here. I know sometimes it's not typing. Okay, let's go inside. Okay. What happened? Pen, laser, pointer. Okay. Now the condition is this. Okay. Another thing that we need to do, we need to save this 10 also. Okay, maybe we need another add I, x10, x0, and 10. So we put x10 also 10, okay? And then we go to the loop. This is the condition, I is smaller than 10. What we check if it's bigger. So bigger or equal, x6 and x10, go to done. because we don't want to repeat it if the condition is not true. We just go to done. Other than that, we just need to add we just need to add x5 1 because it's ACC++, and then add I x6 because x6 is the counter index, so we need to add that to 1, 2, and then jump, unconditional jump, and link x0 and loop. That's it. So this is how we are implementing for loop. Let I just explain a little bit before finishing the code. I don't know why it's not working anyway. Okay, so we are jumping here to loop. This is unconditional loop. So this is ACC++, and this is I++. Why we have I++? Because we have I++ here too. This is the C notation. Okay, so that was good. Let's we have the cleaner version of that. I don't know, my computer I think is not working anymore. Okay, yes, it works. Okay, that's a better version of that. Okay, that's it. We're not gonna go further. Next week we're gonna talk about basic block and